Okay, so let's talk about fusion, shall we? All right. For the first time ever, U.S. scientists at the National Ignition Facility at the Lawrence Livermore National Laboratory in California successfully produced a nuclear fusion reaction, resulting in a net energy gain, a source familiar with the project confirmed to CNN. The U.S. Department of Energy is expected to officially announce the breakthrough Tuesday. The result of the experiment would be a massive step in a decades long quest to unleash an infinite source of clean energy that could help end dependence on fossil fuels. Researchers for decades have attempted to recreate nuclear fusion, replicating the fusion that powers the sun. Okay, so let's talk about why this is a big deal. Oh, I didn't even show. Oh, I'm sorry. Here's the. There you go. There's the page I was reading. Apparently, I didn't click over to it, but whatever. So anyway, let's talk about why nuclear fusion or getting a positive energy gain from nuclear fusion is a big deal. So we have had fusion as a functional technology for a very long time, ever since the Castle Bravo test that the United States set off. That was the first thermonuclear weapon, which is a fusion weapon. So we've had fusion for a while, but the problem is that kind of fusion is massively uncontrolled and hecka boom boom. Yeah, thermonuclear warheads are stupid strong. The largest nuclear test ever done was the Tsar Bomba in Russia, and the shock wave from that explosion set off seismometers around the world three times. I want to say 3 or 4 times. Like the shock wave went around the world 3 or 4 times with enough force that it was being detected on earthquake detectors. The mushroom cloud from the explosion reached space. It was utterly gigantic. So the energy output in a fusion reaction is massive, and we have been struggling for decades now to figure out how to control that reaction like we do with regular nuclear reactors. Regular nuclear reactors are the exact same reaction as the Hiroshima and the Nagasaki bombs in World War II, but we've learned to control it, to slow the reaction down so it doesn't go boom, it just makes heat. And that's what we've been trying to do with fusion forever. And up until recently, the problem has been um, it takes more energy to run the magnetic fields, to run the magnets that produce the magnetic field to contain the reaction. It takes more energy um, to to kick off the reaction with lasers because they have to heat the material up with lasers to get it to fuse. It's taken more energy to power the lasers, and it's taken more energy to run the magnets, and it's taken more energy to run everything in the facility, from the coolant pipes to the pumps to the lights to everything else. Then you get out of the reaction, so you get a net negative um, energy gain up until this point from all fusion reactions. It takes more energy to start it than you get out of it, but they have actually gone positive for the first time, which means that there is a source of energy there. Now, they haven't gotten enough energy out of it to make it commercially viable, but that's not the important part here. The important part is after 50 years of trying, we have finally managed to crack the net positive energy barrier. That just has not been done yet. And it comes from the United States, which is nice. The nuclear, the fusion reactors that were heralded as being the ones that would reach this landmark first, they're not in the United States. So it's nice that this record comes home to where I'm from. You know, I like it when the United States does impressive technological stuff. Um, Outside of computers and software and occasional military equipment, the United States hasn't done a whole lot of really impressive technical things in a while. I mean, the James Webb Space Telescope was amazing. That one was amazing, but um, Yeah, it's just you don't hear about like real American scientific innovation anymore. At least not to this level. And it's nice to see it come home. So, why has it been so hard to get to this point? And the answer is the sun. We're trying to replicate the sun here on Earth, except the sun cheats just a little bit because what happens is the strong force that holds atoms together is actively overpowering the magnetic force that wants to push everything apart. Because, like y'all learned in school, protons are positively charged. That just like putting two positive ends of a magnet together, they do not want to be next to each other. They want to fly apart, right? So there has to be a stronger force holding them together. Otherwise, the atoms wouldn't form. And that's what fusion is trying to do, is trying to get two protons, so positively charged particles, little itty-bitty magnets for all intents and purposes. They're trying to get them to come close enough together that the strong force, which is significantly stronger than the magnetic force, but the range on it is very small. It only works over very tiny distances. So you have to force them together hard enough that they get close enough that the strong force can just grab them and bring them together. And that's very hard to do on Earth. The sun does it because it has massive amounts of mass. The sun is huge. like 100,000 Earths can fit inside the sun. The sun is just ridiculously huge. And as a result, it has all that weight crushing the center of it down to push those atoms together. And it pushes them close enough together and gets them hot enough that the strong force can grab and squish them together. And that's where the energy from the sun comes from. And we're trying to replicate that here, except there's no possible way, literally no possible way, to compress material into a small enough space that it will spontaneously fuse like it does in the sun. So instead, what we have to do is heat it up to ridiculously high temperatures, like significantly higher than the core of the sun. And what is heat but just the random movement of atoms? So the hotter you get your material, which is where the lasers come in, they heat everything up. The hotter you get the material, the more random the movement is, and the wider area the atoms are moving around in. And if you get it hot enough, the area that they'll move around in will have a non-zero chance for two atoms to randomly end up next to each other, and then poof, fusion. Just like in the sun, except you did it with a crazy amount of heat instead of a crazy amount of pressure and a smaller but still crazy amount of heat. Now, we've been able to do that for a while. We've been able to kick off fusion reactions for a long time. The problem is, once you do that, you have to then create an environment where the atoms will keep doing that. So they have to be hot enough, they have to be close enough together, and they have to be contained in a way that they won't destroy the machine that you're putting it in, because there is no metal on Earth that can survive the temperatures that is required to make this happen. So they contain it with magnetic fields. They don't even let the material touch the machine. Otherwise, it would just instantly turn it into goo. And so as a result, they've been trying over the years to try to create this magnetic field that contains the material and keeps it at a high enough temperature that they can keep the reaction going and end up producing positive energy. And it's just been ridiculously hard to overcome that hurdle. And they finally did it. And that's big news. That is big news. That's the first really major breakthrough in fusion since they actually managed to get ignition. And ignition happened like 30 years ago. So this is big news because fusion is essentially limitless fuel, because you're using hydrogen, and hydrogen is literally the most abundant element in the universe. It's like 60% of the universe. Like, we will never run out of hydrogen. It's in everything on Earth, basically. It's in all kinds of compounds. You can get it out of water, you can get it out of compounds in the air, you can get it out of, it's in hydroxides and all kinds of stuff. And so hydrogen is readily available. We can produce it pretty easily with natural gas. And as a result, we could power the entire world pretty easily and cheaply if we could get fusion energy to work. So it's like the holy grail is figuring out how to make fusion work in electricity generation, and we're that much closer, and it's a big deal.